I sort of promised to you to show to a data structure that would sort of support this trapezoidal decomposition that I have done. Okay. Start with a small example and we will see as we go on. Fine. Okay. But the basic nutshell of the algorithm is as follows. A line segment comes, remember that. So, this line segment comes and you figure out the trapezoid it hits into the left hand point using some amount of time, we will see. You understood that there is some amount of complicacy there, but assume that you have been able to locate, and then sort of because of this storage of the subdivision, then you can sort of walk along this line segment as you jump from one face to the other. There are obviously rays that have been shoot, you have to trim them appropriately. That was the idea. Now, see, notice a fact that when you are sort of trimming a short bullet, it would have been problematic if your short lines did span for the entire range of the rectangular box. No, then you had to trim it down to you had to see many line segments to come down, right. But in here, this was the intelligence of it, no, yes, because you had just shoot up, just shoot down. This trimming business is on a constant size, no, fine, remember that. So, let me draw for you this kind of data structure, and then you would sort of things would start having some meaning for you. Say I have this and say, okay, let us first start with this. And say this is my S1, this is my say P, P1, Q1, P1, Q1 are the endpoints of S1. Okay. So, now what I have to do, given a point I have to figure out the trapezoid it is in, fine. So, so what do I keep at the data structure, the root of these data structures? It is a directed acyclic graph, so it can have many roots, fine, but let us start with one. What can be the root of this data structure? The x coordinate of P1, no. So, let me store P1 at the root. So, the x coordinate of P1. So, that means, if a query point comes, I can, based on the x coordinate of P1, I can take a decision whether you go left or you go right. If you go right in here, you have hit a trapezoid. Okay. So, for this DAG, your leaves would be the trapezoids. So, let this be my trapezoid A. So, this is a leaf. So, you have been able to locate a point within your first trapezoid. Next comes whatever is to the left of this zone, no, but this can span till the end of the rectangle. So, first I have to figure out whether it is in this part of the slab or in this part of the slab, right. Now, for that what I do is surely Q1 is to the right of P1. So, this left and right business is okay. Now, in here if your search path goes left or right, if it goes right, you know that this is the trapezoid you are in, fine. So, another leaf shape, let us call it some T. And if you have gone left from q 1, if your search path has gone left from q 1, then you know that you are either in this zone or in this zone. Agreed? Now, in here I said that when you use the segments, you need to be precisely clear of your x coordinates. In here I am. I know that if my search path has gone on this green marked path, then I am to the right of P 1, which is saying about this, and I am to the left of Q 1, and in here the discriminant is on the segment, right. So, these are the types of your nodes. So, when you come to a segment, when you use the segment as your discriminant, then you can make upper and lower decisions on a particular slab that has been divided by this line segment only, right. And then you have as your leaves of this. So, let us call this to be maybe x nodes, and these things which are based on the segments to be the y nodes, and these are the leaves. Okay. So, then S 1 would again have fine. So, I can have the rough idea of a data structure that supports this. Now, let us make it a little bit more, bring in one more segment and sort of make it a little bit more complicated. Okay. Now, let me just give you this diagram, that would be good for you. Now, see earlier this line through Q 1 was full. When this new S 2 comes, you need to trim this line, no. Okay. Right. So, this is your trapezoidal decomposition, and let me sort of to have simile, let us name this face as this D, E, F and G. Okay. So, my data structure goes this way. So, to the right of Q 1 is Q 2, no. So, this would be like this Q 2, S 1, to the left of S 1 is, let me just draw it for you, S 1, to its right is P 2, left is C, P 2's right is S 2, Q 2's left is S 2, Q 2's right is G, S 2's left is E, Now, if you look into this data structure, there is an interesting thing that has happened. Just look into, I mean, though I have redrawn over my earlier drawing, but if you now look into it, and if you look into the this boundary of the data structure. So, you look below. This is the part that has been introduced because of the new addition, right. So, essentially what will happen is, as I go on adding line segment after line segment in an incremental fashion, the length of this tree would grow, but mind you, it would not grow by much. And we would sort of convince you that, so that means now if you think of a query point, so a fixed query point, so your adversary, think of this in an adversarial logic, the query point can be chosen by an adversary, but the adversary does not know, as because you are using randomization, the adversary does not know the order in which you have inserted these line segments. So, what I will try to later on count is by how much depth this point q is falling through this data structure with the addition of each new line segment. And I would convince you that this fall on the expected case would be log n, but I would not claim that in the worst case it is log n. There can be very longish paths which might take linear even, but those of you who have done a little bit of probability and have used Chernoff bounds kind of thing, which sort of essentially bounds the tail, you can also make an argument like that your number of falls for q or the length that q traverses would also stay close to the mean, or rather probabilistically speaking, the probability that it goes away from the mean, which is log n, will be less. You can make these statements precise by saying that it is 1 by polynomial, 1 by this, 1 by that. So, but the essential idea is you can even prove a result which is a bit complicated, and I will not bring it here. You can even show that the expected thing is log n, but the amount of mass away from the mean is also kind of logarithmic. The result away from log n is not too much. So, this the probability of this event, that the search path is of a length more than log n, is a very low probability event. But I will not prove this result, because this needs a little bit of maturity in probability. Essentially, you use this kind of tail inequalities. Okay. So, now you had the Voronoi subdivision, you had DCL, you know you had a data structure to support your subdivision. Similarly, you had a trapezoidal decomposition. Now, you know of a directed acyclic graph kind of data structure that supports your trapezoidal decomposition. Okay. Now, let us start proving results, which would sort of convince to us that we have already convinced to ourselves that the size of this decomposition is linear in the number of line segments inserted. You have appreciated this fact that this decomposition essentially depends on the set that has been that is inserted, right. But notice a fact that if you alter, say you insert S1 first and S2 first, you got this data structure, but if you inserted S2 first and then S1, your data structure might have changed. No? So, though this decomposition would remain the same, but your data structure might change. Okay. So, the first claim that I make is as follows. So, this I ignore for now. So, the proof idea is nothing but so, essentially if you have seen earlier. So, when I had inserted this black line segment, what it was? Locating the left end point, remember, locating the left end point, we will say we will hold this proving this result for let, and then it was walking along this line, and walking along this line essentially meant was trimming the bullet lines, right. So, as many bullet lines have you hit, you have created so many extra new faces, right, and you have created some here at the beginning, some here at the end, but that is constant. No? So, if you have hit really capital K many bullet paths, then K plus constant is what you have done, and these are the only trapezoids that have been newly created. No? What are the new trapezoids created? For a line segment, for each bullet path crossed, it got into a face, split that face into two, right, one new creation, and for the left and for the right there was maybe 4 more extra, taken everything together, fine. So, it is like if it is hit K bullet path, you have created new capital K plus 4. So, it is order of the number of trapezoids created. So, that is the proof, fine. Now, this tells you that if that be the case, then so each insertion is creating this many trapezoids. If I can now prove that this expectation is something, then I know that per insertion you have created, say for example, this is some let it be some value t. So, then that means on the expectation per insertion has added t many new trapezoids, fine, n line segments, a log n query. So, it is n log n plus n into t on the expectation, right, because the first point you have to look at, assume log n, we will prove later. So, n log n for each new query to get into the first trapezoid, then its expectation, if this expectation is some t, so it is n log n plus n into t, fine. So, let us now have to fix is what is this t and what is this log n. So, it is n log n plus t n t, no, n into log n plus t for the first query, right, and that you have to do for all segments, no, right. So, n log n and the number of trapezoid disturbed and created is say t, t for each one. So, n into t. No, I have considered it, right, that was constant. No, I said if k is the number of bullet paths hit, capital K, then k plus 4. So, it is the order of, fine. Yeah, so the total complexity would be n plus this t into say log n, or rather even simpler, let us put it n log n for. So, what is the job? Look at the first point into a thing, how many of them? N log n, each takes log n log n many, and then you sum over all such new creations. So, it is expected t, there are n many, right. So, n log n plus n t. So, if I can fix this log n, convince you about this log n and this t, we are done. Now, what you think should this expectation be? Make a guess. Make a wild guess. Worst? No, I am talking of expectation, man. Log n. Can you not be more ambitious? Yes, yes, I heard it. Yes, let us hope so. Let us see if this works. And this is the lemma that we are going to prove. This is kind of a serious stuff. We will have some combinatorial arguments. So, consider the randomized so if I write RIC, it means randomized incremental construction of a trapezoidal map and let K I be the number of, as earlier, the number of new trapezoids created when the ith segment is added, then expectation of K I is equals to, let us keep this for blank, where the expectation is taken over all permutations of the segments considered till now. Okay. Let us try to do a proof of it. So, for some notations, let T I be the trapezoidal map after I insertions. Mind you, what is this? What is this? Order I, no, right, 6 n plus 4 or 3 n plus something something, the first result that we proved. Right. So, linear, I mean in the number of line segments. So, remember this, I had used this later on, this is order I. Now, what I want? I want to figure out, so to compute this expectation in a very bad way, what can I do? I mean, I look at all random permutations, right. For each one, I see what is the number of trapezoids created at the end, add them all up and then take the average. But again, now we know of a tool, right. We could have fixed a set, done a conditioning over it, but now we have this tool of backward analysis, where I look at the last segment and see what it is doing, fine. Okay. So, essentially you now should appreciate that there is a relation between a segment and a trapezoid. So, a segment is dependent on the trapezoid in some way, or rather the trapezoid, a trapezoid is dependent on segment. Okay. Now, see, so you have a trapezoid, right. So, think of this situation till you have inserted I minus 1 lines and you have a trapezoid. When do you think that, or rather think it this way, you have inserted the ith line, right. You have got a trapezoid, you have got the trapezoidal decomposition and you are looking at a trapezoid. When and only when can this now think of lifting the last line, fine. So, you had the ith line, you had inserted it, you got the trapezoidal decomposition and now you are looking at a trapezoid. And now you think along this question that when and only when can this trapezoid change if I am going to take away my last inserted ith line. If and only if this was one of these 4 lines, no, and that probability is going to be very less, no. This is the logic I will play on. Fine. So, let us say depends on a segment S this is important. So, this is what I mean by depend. So, when I say that this delta depends on S, the segment S, this is what I mean. Fine. So, if this line segment S is the cause for the creation of delta. Okay. Now, I would obviously, as because there are 2 quantities, I would define an indicator random variable let that be this delta this is equals to 1 0 1 if obviously what did I say? S depends on delta, trapezoid delta depends on segment S if delta depends on S 0 otherwise. Okay. Now, what is your expectation of k I? That is easy to see the moment you have got into a 1 0 random variable, right. Now, mind you, S brings in the randomness, no, because what I had done, I had taken the I line segments, permuted it, I am working with this permutation, right. So, S is a random insertion, right. S is one of the I randomly one of the I lines, right? Line segments. Fine. Okay. So, this is my. So, for handling expectations of 1 0 variables are easy. So, this is the quantity. So, you fix a segment. Mind you again this notation you are I think by now familiar. This means the first I line segments. So, this reflection is sort of very bad. I really cannot see, excuse me. So, this reflection does not allow me to see what I am writing. This light's reflection. Anyway, let us continue with this. And this is a trapezoid in T I, right. Mind you, just be careful of the notations. What is this? Tau I is the decomposition created till now, and S I is the line segments inserted till now. So, I am summing over it, and what I am going to sum is this. So, I have to handle this sum. What? This, right. So, I just, what is this? I am adding all this, no. Right. So, what this sum tells you? Fix a segment. Fix a segment. Look at all the trapezoids created by this, right, and then vary it over all segments. This is what? Agreed? No doubts on this? Okay. So, this tells you fix a segment, look at all the trapezoids created and sum over for the probability thing, no, right, because this. So, if you just forget about this 1 by I, then it is the entire sum, and obviously, I look at this S could have been any one of these I lines. So, I multiply it with the probability. So, it is the, so expectation is x into p x, no. So, that is the probability term, fine. So, I mean I am essentially jumping steps. So, you take linearity of expectations, right, and come to this. So, but that is not very difficult to see. Essentially, it is a calculation wise, it is summing up everything divided by the probability, right, or into the probability. Agreed on this term, but this term makes you see fix a line segment and then look at all the trapezoids created by this line segment, vary over it. Fine. But is this a good combinatorial quantity to handle? Because a line segment might perturb many things, it is going to be order ki, then I am not being able to handle it much, it is becoming difficult. If you see in here, for this black line inserted, for this line inserted, it was disturbing a lot, no. Let us figure out that region. So, it was disturbing here, 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 here, a lot. And it depends on, in a way, the length of the segment, no. Because if it is going to span through many, it is going to create a lot of nuisance for me. But think on this, this is kind of an interesting thing. If all are your long segments, would you do badly? No, no. Okay. But in here we use the classical combinatorial trick of double summation. So, when it gets difficult to handle a double summation, what do you do? Change the order of the summands, fine, do it. No, earlier it was red, oh, it was dangerous. So, let it be black now. This is this is this. It remains exactly same, agreed? These two are same. Now, what does this quantity tell you? This quantity tells you fix a trapezoid and vary it over all segments, no. Fix a trapezoid, the outside is fix a trapezoid in the trapezoidal decomposition. Mind you, Ti does not vary. Once the set I is fixed, Ti does not vary. So, I can do that summation, it is not a variable component, fine. Okay. So, I can pick up delta out of this tau I, agreed. Now, what I do is I look at the, I do the sum. This is a easy quantity to handle. What is this quantity? This should be what? this green marked thing. What it is saying? Look at a trapezoid. Look at a trapezoid, and I am looking at the dependency of this trapezoid with line segments. No, this is your delta. It depends only on this 4, no, right. So, this quantity for each one is 1, you sum to 4, agreed? Okay. Do you agree on this? What this is? See, you had fixed a trapezoid. So, this is your fixed trapezoid, and you are looking at the dependence of this trapezoid on your last segments inserted, because this delta of both are delta, no, right, the small delta of capital delta S. This is a quantity of the dependence on this delta on S, where S was the last inserted. That is important. Fine. Okay. So, this is 4, no, because each adds up to 1. So, there can be at most 4. So, where is this sum going? So, I can now forget about right, I can now forget about this, keep this, and this is 4, right. So, this is now 1 by I 4 into tau of I. What is tau of I? Order I. So, this is done. So, we have been able to fix the statement of the lemma. This is order 1. So, the disturbance created by any line segment is on the expectation constant. So, I have convinced you what is this, no. So, I have convinced you about this. What remains is to show you about the logarithmic thing. I mean I think I should have drawn this in a better way. See, these 4 lines essentially comes from where? This or this, no. So, these are the 4 line segments that could have created this delta, agreed. So, what was the vertical length that I drew was essentially the right end point of one line segment and the left end point. So, if any one of these 4 line segments was your last S, then only this trapezoid was created, else not. Done? Okay. Now, what remains is to convince you about the search. Okay. Maybe you can think of this. No, what is happening? No, you can go here. So, this is a question of which you can think. How big can the now see this question needs to be answered, because see the geometric, what we have essentially proved is that this decomposition is linear sized. No, we have not proved that this data structure is also linear sized. it might be so that you in creating your data structure that supports this, in creating your data structure that supports your decomposition, you have not been very efficient. So, then your data structure size might grow, no, there is a possibility. So, you have to argue properly to show that the data, I mean you see, for example, there is a multiple storage of S 2, right. Then there is anything else multiple stored, possibly not in this, but no, F is not, leaves are only the trapezoidal faces are the leaves, in here only F, fine, right, only S 2. But again it cannot be many times, no. And essentially you see what happens is, I will show you with a few case analysis that what is the size of the data structure for each insertion, growth in the data structure for each creation. We have argued that when you inserted the ith line, you only are going to make on the expectation constant size change in the geometric decomposition. I will also convince you that on the data structure side, you will also make constant additions. So, then it also would sum to linear, agreed. So, let us figure out what are the cases that we need to handle, fine. So, one is like the line segment is going to start from a trapezoid. This is the case I have to handle. In that case, a ray has to be shot up, a ray has to be shot below. You have to create a left trapezoid and two trapezoids, one above the line segment, the other, right. Similarly, you have to handle the end case, right. Then again you shoot a ray above, handle it, and the other case is when this line segment goes through a trapezoid. These are the only cases to handle. We will show to you that for each one of the cases, what is the change in the data structure. So, let us quickly do that case analysis. So, the first case is like this one, pink color is visible, no, from back. So, this was possibly your A, this was your trapezoid, and this is your new line segment created S. This is P and this was your A earlier. So, what is your change in the structure? So, the change in the structure is no, this, right. So, change in the structure is this. Okay. So, your earlier thing was for the data structure, you had something coming to a leaf of A, right. Now, you are going to replace it as, you start with what you should do. So, earlier it was A, only a trapezoid, no. So, your point location would come to this trapezoid. Now, once it gets into it, it has to distinguish between whether I am to the left of P or right of P. If I am right of P, then I should distinguish whether I am above S or below S. That is what I handle in the data structure. So, quickly this is your change. Let me call this x, this to be y, this to be z. So, this is your x, this is your, in here you would come your y node S, and then here you have your y and z, right. Agreed. Now, see what is the amount of addition to the data structure, constant, no. This is one case. The second case is and you have your new line segment as completely lying inside. Fine, this can be a case. Okay. In that case, what was earlier your A now would be, you have to shoot rays like this, A gets changed to U, Y, Z, X, and this is your P and this is your Q. So, what was earlier only A gets changed to, quickly let us draw it, it is P, to the left is U, to the right it is Q, then I have the line segment, the Y node, line segment, and this is Y, this is Z, and this is X. Again a constant addition to the data structure, right. Next case, this one that we saw. So, this was your kind of case 2, this was your case 1 and this is your case 3. This is this and this is about this passing through. So, sorry. So, this was your earlier thing. Now, it is what was A is being split into 2, maybe B and C. This is easy to do. So, what was your earlier A gets changed to, this is the easiest case to handle. So, you will have just sorry, you will have Y node for a segment and to its left you have B, to its right you have possibly C. Right, again a constant addition, and you can convince yourself that these are the only 3 cases. Fine. So, we have convinced ourselves that the data structure is also linear sized. So, remember this question that we posed ourselves, this is also linear, no? Fine. Now, about the query analysis, that would finish the game. So, consider a query point Q. That say has been fixed by an adversary. So, as I was telling you that this is a data structure which is evolving. So, I have a fixed query point and I will see how this query, I mean, now see essentially what is happening. You have fixed a query point and there are these I lines which are you are randomly inserting. So, what will happen is, what will keep happening is, think of a new line segment, no? When a new line segment comes, you look at its left point, and when you look at its left point, it keeps falling through this data structure, right. It will keep falling through this data structure till it gets to a leaf, till it gets to one of these leaves, and then it sort of adds something new to this leaf to create again a constant sized extra number of neurons, and then it falls that much to get into the correct trapezoid where it has belonged, right. Okay. So, my point q is fixed. The saving grace for our analysis is the adversary does not know the random order in which I am inserting these I lines, otherwise he could have made my life hell, right. So, the adversary picks this point, but what is in my hand is the random order in which I insert it. So, the adversary will not win almost always, no. I have chances of winning. Okay. So, this is the case of the analysis. So, by an adversary, so let us make this clear, without the knowledge of the random order in which we insert the lines. So, the data structure is not fixed, it is evolving and I am doing my analysis on this. Okay. So, let me define my this probability P I. It is the probability of the event that the trapezoid that contains Q changes as a result of the ith insertion. So, probability of the event that the trapezoid that contains Q changes as a result of the ith insertion. So, if you look into the basic data structure, sixth one, right. So, as this point Q falls through and it has gone into a trapezoid, it will not increase its depth until and unless this trapezoid C was not created at this instance. No? If it was created at an earlier instance, it is not going to change, whatever length it had fallen till tau I minus 1. So, you look at the point Q, no? Think of this history. Look at that point Q and consider tau, capital tau I minus 1. It is the trapezoidal decomposition after you have inserted I minus 1 lines. Now, see, this point Q will trace some path to the sum of the leaves of this trapezoidal decomposition. When will it fall further? If and only if this trapezoid breaks into some new trapezoids, else it will remain the same. Say for example, if my query point is at A, it is not going to fall any further, no? And the next comes there, right? Okay. So, I am basically going to argue over this length, sum of this fall at each insertion. And you have now seen that the fall will only happen if the trapezoid into which it belonged for capital tau I minus 1 had changed after the ith insertion, and that probability you have already argued is very low. Fine. So, now we will just do a little bit of summing up over expectations and then we will be home. Okay. Again come back here and just, so we are done almost, 2 minutes to the final result. Agreed? Now, each fall, so here the length is a fall by 1, really does not matter. Let us look at the largest fall. Here the fall is by length of kind of 3. No. Yeah, here the fall is by 2. So, the maximum a fall there can be a fall of 3 constant size. Okay, fine. Okay, so let us compute this expectation. Expected length of Q's search path in the final structure is at most agreed. Expectation maximum I have taken 3, that is the maximum fall that you can have, and pi is the probability. So, I need to just figure out what is pi. Backward analysis. What is pi? We have done this earlier, no? Will fall if this trapezoid, if any one of this or this was the last created, last inserted lines. So, 4 is your favorable, and in all you have I many. So, this is now summing to 3 by I equals to 1 to n 4 by I, and you know that summation of 1 by I is kind of a harmonic series. So, you would get to say 12 log n. So, now as I said, I mean though I have not written, but this you can argue using backward analysis. Anything more to say? No. Okay. So, I finish with a caveat. So, the caveat is what I said, this is an expected result, remember it. I am not claiming like you could claim for your search in a balanced binary search tree that the worst case is even log n. I am not claiming that the worst case is log n, because it might so happen that at each instance the query falls by a 3. No? So, what I am claiming is that the expected thing is log n, right. So, plus 10 and minus 10 makes the average 0, but plus 1 and minus 1 also makes it. So, a good distribution is kind of a good distribution is one which is spread around the mean. So, in here using, as I said, tail inequalities, you can show that the probability of this expected length of the length of the search path going over the expectation, which is log n, is a low probability event, right. So, I mean if you are not conversant with Chernoff bounds and stuff like that, it is difficult to make it precise mathematical, but you can get with this notion that you can prove a result which tells you that the not the expected, the length of Q's path in the final search structure is more than its expectation. So, it is x minus expectation of x, this probability is bounded. So, essentially one can even show a result like this, which I am not proving. So, let x be the path length of q, let this be its expectation, right. I look at this and I take the probability of this, and one can show that this is going to be bounded by a small quantity.
Chernow bound is used to justify that boundary.
Right. To show that those kind of. So, there are many kinds of tail inequalities. Chernow bound is one of them. There is to start with, there is Markov, Chebyshev's, and as your events and dependencies, this gets complicated. You have to use more advanced kinds of tail inequalities. Fine. One can even prove a result that is a low probability. So, it is not that you are going to deviate from the expectation many times. You can deviate, but not by much. Okay. So, I would end here.